Hello, good morning, students. You are welcome to the AAE 468 Advanced Orbital Mechanics class. Today is the 31st of January 2015, and the time over here is 9:47 a.m. I believe you have gone through the slides on AAE 313. Orbital Mechanics 1, as I suggested you should do, because Orbital Mechanics 1A 313 is a strong prerequisite for this course. So you need to go and revise your slides if you haven't done that already. So we'll be starting this class with orbits in 3 dimensions. Of course, you know what orbits are. An orbit is a path of a body around another body, particularly of spacecrafts or planets around another body, and it's usually a curved path. So if you try to look at Google Earth here, we see that we've got the Earth there, and if I just try to put the sun somewhere, then we try to see what it might feel like in real life to see the Earth go around in orbit around the sun. I'm still trying to search for the sun. Yeah, that's the sun there. So the Earth, we know, orbits the sun. So that means it goes around the sun in that manner. And while it's going around the sun, it's also rotating about its own axis. And that is what brings about night and day. Right now, you are getting nearer to the evening, almost getting to the point where to start getting dark. And I, over here, just woke up not too long ago. So, and the rest of the space here is just space. That means even the Earth is in space. Space is just a vast expanse where everything is located. Everything that is planets, stars, asteroids, meteoroids, everything that is ever created or that is ever present in the universe, where everything is located. So we are just on the surface of the Earth. So with that said, we go back to our slide, and then we move on. Yeah, the bulk of the material from this slide is from the reference text, Orbital Mechanics for Engineering Students. I know Kwasu Library has got the latest edition of this textbook. I've also got my own copy of the latest edition as well, Orbital Mechanics for Engineering Students, 3rd edition by Howard Curtis. We will occasionally be making references to this latest edition. So I advise and suggest that you always, if you can borrow the hard copy from the library for your use, then it will be good. If you can't borrow it, it's always go there to consult it. So we'll move on. And I should say, usually, you know, as I always took my lectures, I prepared the slides before the lectures, maybe like 2 hours before the lectures. But even right now over here, I don't have the time to prepare the slides way before the lectures. So some of these videos will be taken just about when I'm making the slides, so that as I'm making the slides, I'm also already lecturing. And so it might give you an insight to how I make my slides, and I hope it won't be boring, but it will be interesting. For this part of the beginning part of the course, since I just took over some portions of the slides which I gave you already for AAE and incorporated them into this present slide. That means I have some already made slides to show you now, but occasionally in between I might be modifying the slides or doing adding some other things, updating the slide. So the soft copy of this textbook, Orbital Mechanics for Engineering Students, I mean the one that I gave to you, I'll also be making references to it in this video lecture. So we know that our discussions so far on orbital mechanics AAE 313 was confined to the orbital plane. That is, everything we were talking about was just in 2 dimensions: the orbital plane, the gravitating body, and then the orbiting body were all, their motions were all in the orbital plane, confined to 2 dimensions. So this presentation will present the means of describing such orbits which we studied in 2 dimensions, now in 3-dimensional space, which is of course the setting for real missions and orbital maneuvers. It will also conclude with a bit of a summary of the 2 major disturbances of Earth orbits due to the Earth's non-spherical shape, which will by then refer to as the effect of the obliqueness of the Earth. Because the Earth is not a perfect sphere, it's got some bulging at its equator. So such physical shape of the Earth, or such deviation of the physical shape of the Earth from the perfect sphere, have some effect on the on the 2 body motion that we were studying in AAE 313. So we'll look at what such effects have and how such effects have been utilized to place some satellites. So yeah, I think this is where I might want to go to the PDF, because I just don't want to start typing any other thing besides what the textbook did. The textbook has done quite well. I just don't know what else I could put. That's why I just snip the page and put there. So I think I'll just go right to the textbook and try to just read through. I won't be reading out for most of the time, but I hope you will be reading if either the PDF on your own computer or as it is showing here, but you will be reading in WhatsApp. So occasionally I might just read it out. If I have some kind of comments, I might just say it out too. So we see that of course the chapter that we are on is chapter 4, and it's orbits in 3 dimensions. That's the outline of the chapter: introduction, geocentric, right ascension, declination frame, state vector and the geocentric vectorial frame, orbital elements and state vector, coordinate transformation between geocentric, equatorial and perifocal frames, effects of the Earth's obliqueness. I hope you still remember what a perifocal frame is. A perifocal frame is just a natural frame of reference of the orbit. It is just coincident with the orbital plane, and such words as, or such it's a word as geocentric. I hope you know what it means. It just means it's centered at the Earth. Other things I hope are also familiar to you. Right ascension and declination might not be as familiar to you as one would hope they will be at the end of this video lecture. So we move on to start reading. I might just read the first paragraph so that you get along with the speed with which I'm going to be reading in words. So I start. Introduction. The discussion of orbital mechanics up to now has been confined to two dimensions, that is, to the plane of the orbits themselves. This chapter explores the means of describing orbits in three-dimensional space, which of course is a setting for real missions and orbital maneuvers. Our focus will be on the orbits of Earth satellites, but the applications are to any two-body trajectories, including the interplanetary missions we discussed in Chapter 8. Well, at this juncture, I think I might just want to quickly search over the internet if I can get a very nice picture which shows which probably depicts satellites in orbit around the Earth. So let's see if we can get some. Yeah, there are some. So these are quite interesting. I would hope we don't have as this much satellites all around the Earth. It looks chaotic. Okay, I'm looking for one that is not too. Okay, let's use this one for now. So this is what we are talking about. Here we have like how many satellites around the Earth? 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are all in their own particular orbits. No, sorry. I think they might just be 1, 2. I need to just count the orbits because the picture shows a satellite on its own orbit twice. So the number of satellites here are just 1, 2, 3, 4. Yes, because there are just 4 orbits. So what is interesting here is the fact that we have the Earth there as a sphere, and the Earth, of course, is in 3 dimensions. And then our discussion of orbits in A313 was centered on, if we were considering just one of these orbits, just the plane of this orbit there. We weren't considering anything which might be, or the orientation of the orbits with some other region away from the plane that the orbit was describing. But you see that for us to be able to actually understand or be able to put anything in orbit around the Earth, we need to find a way to describe such orbits in 3 dimensions so that we'll be able to know how it is oriented in space or how such orbits will be different from some other orbits around the Earth. Because yes, we have lots and lots of satellites in orbit around the Earth. So you can check on for more interesting pictures on the internet, which will bring our discussion into better light to you. But this is quite illustrative. So if we go back to our PDF and we continue reading. So I'm just going to read the first sentence of the next paragraph, and then I'll be reading in words. I hope you'll also be following by reading in words. We begin with the discussion of the ancient concept of the celestial sphere and the use of right ascension and declination to define the location of stars, planets, and other celestial objects on the sphere. Well, I might just read the next sentence out because it seems to be interesting to me. Or I want to remind you of something that we might have learned before. So this leads to the establishment of the inertial geocentric equatorial frame of reference and the concept of state vector. I hope you still remember that when we defined an inertial frame of reference, we said it's a frame of reference that does not have any translational or rotational acceleration, acceleration as being the keyword, with relative to the fixed task. That means we are looking at kinematic quantities. Reference to such a frame of reference would have their absolute values. So now we say we said from this sentence, it says we'll be establishing an inertial geocentric equatorial frame of reference. That means the inertia, it's not moving related to the fixed as geocentric, it is fixed to the center of the earth. Equatorial, that means its plane is just with the plane of the equator of the earth, frame of reference. And then the concept of state vectors. Yeah, in AAE 313, we got familiar with state vectors, and we said the state vectors are just the position, velocity, and acceleration vectors. So we move on. The 6 components of this vector give the instantaneous position, velocity, and velocity of an object relative to the inertial frame, and define the characteristics of the orbit. Yeah. When you hear the word sun synchronous orbit, well, we'll get to know what that means much more technically later on. But what comes to mind immediately is the fact that the satellite, which is in a sun synchronous orbit, or which is called the sun synchronous satellite, must be in sync with the motion of the Earth. With the motion of the sun. That means you should follow in just layman terms. We'll get to see what it means much more, the technical meaning later on, but just from the words, that means the satellite is in synchrony with the sun. So geocentric right ascension and declination frame. So the ecliptic is the plane of the Earth's orbit around the Sun, as illustrated in figure 4.1. So if I just quickly go to the internet to try to get a better picture, which might be used to explain what the ecliptic plane means. That doesn't show it now. Yeah. This shows it well. Yeah, so what it just means then is that if you were to have like a very advanced view of the orbital plane of the Earth around the Sun, this is what you would see. So that's the Sun as one of the foci, and then that's the orbital plane. So in 2 dimensions, we are looking at the orbital plane of the Earth. So what we are now saying is the ecliptic, that's the ecliptic plane, the orbital plane of the Earth, that's the ecliptic plane. It's not perfectly coincident with the equatorial plane of the Earth. That is, the equator is inclined to the ecliptic plane by this amount, 23.5 degrees. So if the equatorial plane and the ecliptic plane were to align and then be parallel, then that means the North Pole, this North Pole would have moved to this direction, and then the equatorial plane there would just be on the ecliptic plane. So the equatorial plane is different from the ecliptic plane. So the ecliptic plane is just the orbital plane of the Earth's revolution around the Sun, and then the equatorial plane, of course, is just that plane which divides the Earth into 2 hemispheres, the northern and then the southern hemisphere. But as the Earth revolves around the ecliptic plane, it keeps the equatorial plane keeps what I want to say is the angle here keeps closing up and then opening up on the other part. That means the equatorial plane at some point will coincide with the ecliptic plane, and then at some point will also be tilted to this side of the ecliptic plane, and that's what brings about the changes in the season most noticeable in the very northern hemisphere or the very southern hemisphere. So we go on. So the ecliptic is the plane of the Earth's orbit around the Sun, as I just explained with those pictures. The Earth's axis of rotation, which passes through the north and south poles, is not perpendicular to the ecliptic, as I just showed. It is tilted away by an angle known as the obliquity of the ecliptic, small eta. So the 23.5 degrees or 23.4 degrees, which I showed you, if I just quickly go back to it again, this is the obliquity of the ecliptic plane. Therefore, so we go on. Therefore, the Earth's equatorial plane and the ecliptic intersect along a line which is known as the vernal equinox line. So, the vernal equinox line is the point where, so at that point where the equatorial plane and then the ecliptic plane coincide, then that point is called the vernal equinox line. Let me look for a better picture to show the vernal equinox line. And maybe that one is. Yeah, this one is, I think. So I think this one is, so yeah, so that's the ecliptic plane. And then here we'll see that the celestial equator is just parallel to the um, the equatorial plane of the Earth later on. But just for now, take it from me that the celestial equator is parallel and coincident with the geocentric equatorial plane. So that means the point where the equatorial plane coincides with the ecliptic plane is the vernal equinox line. So if we draw a line right from the center of the Earth out up through that point and away from the celestial sphere, that line is called the vernal equinox line. So the vernal equinox line is the point where the ecliptic plane, which is the plane of the Earth's orbit around the Sun, coincides with the equatorial plane. So that's the vernal equinox line. On the calendar, vernal equinox is the first day of spring in the northern hemisphere, when the noontime sun crosses the equator from south to north. So, and it's usually around the 21st of March. So the vernal equinox is symbolized by the Greek letter gamma. So, and because the sun, on the first day of spring, when the ecliptic plane and then the equatorial plane coincide at noon, when the sun is just crossing the equatorial plane, that position is the vernal equinox line, symbolized by the Greek letter gamma. And on that day, the number of hours of daylight and darkness is equal, most noticeably in countries where the number of hours of daylight and night vary a lot. Around the equator, we don't usually see much variations in the hours of daylight and night, but put it in mind and try to start counting or noticing the length of the day now, and then when it's moving towards the 21st of March, or precisely on the 21st of March, try to count the number of hours of day and then the number of hours of night, and try to see if they are actually equal. It should be fairly around 12 hours of day, 12 hours of darkness in Nigeria around the equator then. So we continue. And because on the day when the ecliptic and then the equatorial plane coincide, we have equal number of hours for day and night. That's why the name equinox arose. The other equinox occurs precisely 1/2 year later. So let's see what constellation Pisces is. You do know what constellation of stars mean. Let's try to see if we also can see the constellation Pisces in our night sky over there in Nigeria. So if we are able to get a picture, I want you to look out for it in the night sky. So that's a picture for constellation pieces. Can one really make this out? The next time you look at the night sky, try to see if you are able to see this constellation. Or let's see a better image it might. Yeah, try to see if you can see this constellation. Okay, and this image just shows why it's called pieces. Oh, so try to observe the night sky and try to see if you can see this pattern of stars, and that would be the constellation pieces. And then you know that that is the position of the lunar equinox. Or it's visible in the night sky during the fall. Fall is around August, September, so you may not be able to see it now. So this is interesting. You see, for many practical purposes, the lunar equinox line may be considered fixed in space. However, it actually rotates slowly because the Earth's tilted spin axis precesses westward around the normal to the ecliptic. When you say something precesses, that means it's um, slowly rotating in the manner that I'm rotating this uh, uh, pen. So it's slowly doing something like that. Notice that this other end of the pen is not moving away from the let's call it original point, but this other end is making out a form of circular path. So that's what precession means. So what we are seeing from there is that the tilted, because the Earth's tilted spin axis is precesses westward around the normal to the ecliptic at the rate of 1.4 degree per century. So yeah, that is it. This is the spin axis of the Earth, and it is tilted to the ecliptic by the obliquity. So it precesses around the normal to the ecliptic. That means it moves westward. It precesses westward. That means it moves around like that, with, of course, the center of the Earth staying almost at one single position, but this line moving around the normal to the ecliptic. And we'll see why that is the case. So it's interesting to see that it's almost like forming out an imaginary cone. So we see why that is the case. So the rate at which it precesses is 1.4 degree per century. This slow precession is due primarily to the action of the sun and the moon on the non-spherical distribution of mass within the Earth. I hope you are reading along as I'm moving the cursor. So from here, let's go to the picture and I'll try to explain a bit. So we know the Earth is in motion around the Sun. So if the Sun were to this were to the right of the Earth, then the Earth would be moving in this manner. And we know there's a gravitational force of attraction from the Sun, and that is what keeps the Earth in orbit and every other planet in orbit around the Sun. So the dominant force of attraction is towards the center of the Earth, and that's the one that has been denoted in F. But then we know, because if you have something spinning like that, gradually the mass, if it's a bulk of mass and it's spinning, the bulk of mass will be concentrated at the equatorial plane. So that means because the Earth is spinning about its own axis, the effect is to kind of like bulge the equatorial regions of the Earth. So that means the equatorial diameter is a bit longer than the polar diameter. And what this means then is that the mass, the region of mass over here is closer to the Sun than the region of mass over there is at this instant in time that we are looking at. That means this portion of mass is going to be experiencing much more on a local level, much stronger gravitational pull from the Sun, because of course we know that the gravitational force of attraction is the inverse of the distance apart, the square of the distance apart, so that when the distance apart is small, then the force of attraction is greater. When the distance apart is big, then the force of attraction is lesser. So that means this portion of the Earth will be experiencing much greater force locally than this portion will be experiencing. And once we have some force imbalance around a center, you know you have some kind of movement. So it's like some kind of torque would now be induced, which would want to close up this angle between the equatorial plane and then the ecliptic plane. Of course, that is visible enough if this force is pulling this side of the Earth, trying to bring it down here, and that is also pulling it to that side. The effect would want to be to close up the angle there, which is also the angle there. So if the Earth were not spinning, if it were not spinning, that would have been the case. This angle would have been closed up. That means the equatorial plane would have just been pulled so that it will coincide with the ecliptic plane. But then the Earth is spinning, and we know it's spinning, and because of its spin, there's an angular velocity vector which is directed to the the north pole of the Earth. I know, you know, when something is spinning, when you apply some force to it, it's kind of like stabilizes. That's the principle of a gyroscope. So we'll see a video shortly. So because the Earth is spinning, it doesn't allow the ecliptic plane to close up with the equatorial plane. But what then happens, because this is still the moment generated is still there, what then happens is the axis of the Earth's spin now precesses around the normal to the ecliptic. That means it will be moving around the normal to the ecliptic. In order to explain this better, I'll try to play this video of a gyroscope. I think you should have it already, but if you don't, I might be able to send it to you. Or you could ask from your juniors, the ones in 300 level now. Let's see. And I think it must have been downloaded from the internet. I may not be able to play the whole video, but then it's just a part that is interesting.
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel.
So if I just pause there, now in order to be able to understand what we've been talking about better, imagine that the Earth is now this portion of the spinning portion of the gyroscope. Imagine there was some kind of sphere here, which started spinning as soon as the rope was drawn. So
the first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when.
So because now this portion is spinning, it's going to be resisting any force that wants to change its position, and that is what we've been talking about. Because the Earth is spinning and spinning that way, because it is spinning and spinning, the effect of this force is trying to change its position, trying to close up this obliquity, will be resisted by the Earth because of its spinning.
I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright.
This is exactly similar to what I've been trying to explain. You see, because of the force of gravity, if this were not spinning, it would just fall over. That is, some force will just, of course, the force of gravity will attract maybe this portion to the ground or that portion to the ground. But because the gyroscope is now spinning, and then the angular velocity vector is directed into the normal to the spinning, the plane of the spinning, then the gyroscope rather resists the action of the force trying to pull it down. But because the force is still acting, the gyroscope is now rather precessing about the angle normal to the plane of where the force is coming from. So that's the
wheel stops, the force disappears and the gyroscope falls.
You see, if the Earth were to stop spinning, that means it will just respond to the forces trying to bring it down. But because it is still spinning, it will just be precessing about this axis normal to the ecliptic plane, where the forces trying to change its position reside. Yeah. So the spinning Earth is just like
Incredibly,
a gyroscope.
this force will support the gyroscope like this.
Look at
It
this.
appears to be levitating.
And this is just also because it is still spinning. So even the force of gravity is not enough to bring it down just because it is spinning. So it will rather be
The
precessing.
spinning gyroscope will balance on a string.
Yeah. So I'll probably try to send you this video, or you can set it up on Google and download it, or you can ask from your juniors to let you have it. So going forward, so that means if this is precessing, it also means that the line on which the ecliptic and the equatorial plane coincide would also be precessing about will be precessing about some points. We'll be forming this kind of cone around some other points. Let's say this is towards the sun. Let's say away from the sun. I know, but the position of the sun on the first day of equinox signifies the vernal equinox line. So that means if we were to bring this down to simulate the coincidence of the ecliptic and then the equatorial plane on the first day of spring, then if the sun were here, then this would be the vernal equinox line. So what we are trying to say now is because of the precision of the Earth's angular momentum, angular velocity axis around this normal to the ecliptic, the vernal equinox line will also be moving in a kind of precession, about some point. So that means the vernal equinox line is not is not fixed in the night sky or in the sky. It's not fixed. So we just continue then. The moon exerts a torque on the Earth for the same reason as what we just explained here. And the combined effect of the sun and the moon is a precession of the spin axis, and hence gamma, that's the vernal equinox line, with a period of about 26,000 years. You might wonder why one wants to be concerned about something that has a period of 26,000 years. Or if you were to want to plan a mission to Mars, or like a mission beyond the solar system, which would last for many years, or just like the Rosetta mission, which was launched, the Rosetta spacecraft, which was launched about 10 years ago and just reached its target 10 years later last year. That means you have to take into account the fact that things out there are always on the move. If you have an error of an error in calculation, you might just miss whatever the target body is. That means the spacecraft you are sending might just get there a little too late or a little too early. A little too late or a little too early means it just misses its target. So we need to be bothered or to be concerned about precision of all these kind of things. The moon's action also superimposes a small limitation on the precession. This causes the obliquity to vary with a maximum amplitude of 0.0025 degree over a period of 18.6 years. You would have noticed that the book here quotes the obliquity to be 23.4 degrees. Where is it? Yeah, 23.4 degrees. But when I checked somewhere on the internet, or maybe that was from my memory of geography, and we always said the Earth is tilted at some angle 23.5 degrees. Well, what it just means is that the 23.4 degrees is also always changing, and the period of its change is 18.6 years. For 4,000 years ago, when the first recorded astronomical observations were being made, Gamma was located in the constellation Aries, the ram. The Greek letter Gamma is a descendant of the ancient Babylonian symbol resembling the head of the ram. So that explains to us why they are choosing the Greek letter Gamma to represent the vernal equinox line. So we go on, and this is a celestial sphere which we shall be talking about shortly. And let's read what's written there. So we see that the north and south poles of the fixed sphere correspond to those of the Earth rotating within it. The projection of the Earth's equatorial plane outward onto the celestial sphere defines the celestial equator. Just like I said before, the celestial equatorial plane coincides with the geocentric equatorial plane, that is the Earth's equatorial plane. So here in this is the celestial sphere, and that's the Earth at the middle of the celestial sphere, with the celestial equator coinciding with the Earth's equator there. So since if you look up into the night sky, of course, that's what you're going to be seeing. Like, it's going to feel as if there's this huge sphere in which the Earth is enclosed, and then you can try to now position every other thing with respect to the center of the Earth. So that's the celestial sphere, just like a huge giant sphere or ball covering the whole of the Earth, and everything is now located in that sphere. Of course, it would be difficult to have like what do I call it? The extent of the vastness of such a sphere, it just goes to wherever you want to it to get to. So it's just that very vast sphere around the whole of the Earth. So the projection of the Earth's equatorial plane outward onto the celestial sphere defines the celestial equator. The vernal equinox Gamma, which lies on the celestial equator, is the origin for measurement of longitude. So in this diagram of the celestial sphere, the Earth is that in the middle, and then the vernal equinox line, that is the line on which the ecliptic plane and then the equatorial plane of the Earth coincide. That's the one that is shown here. And then if we're trying to now measure lines of longitude, we measure it positive to the right of the vernal equinox line. So in much the same way as we say the Greenwich meridian line is 0 degrees as London, and then Nigeria is some kind of degrees to the right or to the east of the Greenwich meridian line. That is, they're trying to measure the latitude and longitudes of places around the world with reference to some point. That is the same thing we are going to be doing for locations of celestial objects relative to the vernal equinox line. So lines of, if you like it, call it longitudinal lines on the celestial sphere, now are used to determine the right ascension. So when you're talking about the right ascension, you are just talking about the longitudinal distance, if you like, from in degrees. Sorry, you see that it's usually measured in hours and minutes from the vernal equinox line. So if we just continue reading, so the vernal equinox gamma, which lies on the celestial equator, which in astronomical terms is called right ascension. Right ascension. So now we understand what right ascension means. So right ascension can either be denoted by capital RA or alpha. So, and it is measured in degrees east from the vernal equinox. So, degrees east of the vernal equinox. Degrees east of the vernal equinox. So latitude on the celestial sphere is called declination. So these are lines of latitude on the celestial sphere and all that, and then they are called declination. So declination is either capital DEC or delta. And it's positive to the north of the equator and negative to the south of the equator. So this figure shows how the heavenly bodies appear on the night sky. We see here that this is the celestial equator, and then that's the celestial, the ecliptic plane. So the point at which they coincide gives us the point of vernal equinox line. So we notice here that the sun has been put on that vernal equinox line, and it must be that this night sky was charted on the first day of spring, or this sky, it could be that it wasn't in the night. This sky was charted on the first day of spring, and that's what it says there. Notice that the sun is located at the intersection of the equatorial and ecliptic planes, so this must be the first day of spring. Stars are so far away from the Earth that their positions relative to each other appear stationary on the celestial sphere. And that is the main reason of defining an inertial frame of reference as that which does not have any translational or rotational acceleration relative to the fixed stars, because we know those stars are very, very far away, and then that their positions do not really change that much, so they appear stationary. So for every other thing that is near to us that is moving, it appears to be much logical to use things that appear to be stationary as a reference of any measurement of motion. So ephemeris means the coordinates of celestial bodies as a function of time. So table 4.1 gives the ephemeris, that is the coordinates of celestial bodies of Venus and the Moon as a function of time. So if we go to so we see that for a given date, the right ascension of Venus has been put down, and then the declination has been put down. Then for Moon, the right ascension and then the declination. And this has been done for a number of dates. So this is an ephemeris of Venus and the Moon. An ephemeris depends on the location of the vernal equinox at a given time or epoch. Of course, since the right ascension and then the declination are measured reference to the vernal equinox line. If the vernal equinox line is also moving, and that means these are dependent on whatever vernal equinox that has been used to measure or compute them. For we know that even the positions of the stars relative to the equinox change slowly with time. So everything is in constant motion. Nothing is per se in a very stationary state. There was a time when it was thought that the sun was fixed at a fixed position, but of course now we know that it's also moving as the Earth is evolving and the planets are evolving. And well, let's even start from the Moon. As the Moon is revolving around the Earth's moon system is revolving around the Sun. The solar system, that is the Sun with all of the other things revolving around it, are also revolving around some other center somewhere, and that center is also revolving around some other center somewhere. So in fact, maybe we should try to look at Google Earth and see sky. So we go to sky. I do not change. Sky. Yeah. So this is Google Sky. I'm sure you already recognize what this is. This is the Milky Way galaxy, the galaxy in which our solar system is. So our solar system must be maybe a single speck there. Let's see. Let's see. I would think someone might have put the position of the solar system somewhere. But then this is a Milky Way galaxy, and before we delve into the Milky Way galaxy, it might be interesting to see what the Milky Way galaxy might look like if we went further away from it. You see, as we are going further away from it, it's turning to a very single speck where there are other specks somewhere else too. And then we go further, and further out. This is certainly not the end of the universe, but this is probably the end of the humanly charted universe. Of course, we know it's still so huge and it's still so huge that we probably will never know the extent of the vastness of the whole universe. But then, if we try to go back in and then go to the Milky Way galaxy, that's just the Milky Way galaxy somewhere, or that's the center of the Milky Way galaxy, or somewhere there, or there, we might be able to find our own solar system. And then if we now go further into the solar system, we might then be able to find our own planet, Earth. So we can see that everything is so small on that level. And I think there's still one more thing that might be interesting for you guys to see. I hope not this one.
Adventure Quest Worlds, a multiplayer game that plays in your web browser in the ongoing battle between vampires.
Not that one. Sorry about that. It's yeah, this one. I used it yesterday. So this also shows the scale of the universe. Yeah, and it tries to relate the scale that we know it to be on the human scale, like around here. This is like the human scale, and then we can go steps further beyond the human scale. That is going into the very microscopic, and then we can go away from the human scale, like bigger than the human scale. So before we go to bigger than the human scale, it might be interesting to see what lies below the human scale. So I won't be talking so much. I won't be talking so much. I'll just be moving the cursor inwards and outwards until we will have been able to observe most of the skills. And then when we get to where I want you to see, we are going to switch back to the lecture. So enjoy the music. Look at an interesting thing here. If there were, one could probably make an analogy of our planet to be to be similar to what happens on the atomic level. On the atomic level, we know that electrons are constantly moving around the nucleus. So if the nucleus were to be taken to be the sun, then this might also be taken to be planets moving around the sun. So for all you know, there are some things with some kind of life form living on the electrons and seeing the nucleus as their own sun. Who knows? But this is what we have, or almost similar to what we have in space, like on the more gigantic level. So we try to see we are moving outwards, 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 outwards. I'll probably just play the music back on. We are getting to the very gigantic scales. So look at what we are seeing here. The sun is very, very huge and gigantic. Seems very gigantic to us. And we might even think there are, okay, if looking at Google Earth here, and let me try to put the sun. So I'm trying to find the sun. Yeah, so that's the sun there. We see it as very, very huge relative to these other tiny stars. Of course, we know that the sun looks so huge because it's nearer to us. Some of these stars are in fact bigger than the sun, as we would see in this. So that's the sun there. And look, that's another kind of star there. It's not as big as the sun. That's Alpha Centauri A is about the same size as the sun, almost about the same size as the sun. We'll look at Sirius. Look at Sirius A. It's bigger than the sun. But when you look at, if you're able to point out the position of Sirius, in the night sky, you see it as very tiny. Or look at the sun there. There's another star. Those are other stars. You see, look at the sun as a speck, but look at this one here. So huge and gigantic. A lot of times, maybe millions of times bigger than the sun. And then look, there are even other stars which are billions of times, or only God knows, look at the number of zeros, bigger than the sun. And then there are even other ones, and then look the way everything is. So you see, it's almost, if we are coming from this scale and going inwards, it would be as if we are going to the atomic level before we arrive at our own solar system, and then on our own Earth, and then now having human beings living on the Earth. So it's almost as synonymous as to imagining that you have some kind of life around the electrons moving around the nucleus of the atom. So we go even further and further out, you see, that's the Milky Way galaxy. That's the scale of the Milky Way galaxy. You see that there are even some other galaxies which are bigger than the Milky Way galaxy. Look at the amount of things or amount of length scales that we've had to come before we even got to the length scale of the Milky Way galaxy. And the Milky Way galaxy is even a very tiny speck in the whole location of things. Look. So we get to the observable part of the universe. That is what we've been able to observe. There might still be some other things around these portions, or even bigger than all these portions that we've not been able to, or we might never be able to chart because of our limited human capabilities. God is indeed wonderful. So let's go back to our study. So we know that even the positions of the stars relative to the equinox change slowly with time. So everything from what we've been looking at, everything is always in constant motion. Everything is in constant motion. So those stars that are very fixed to us are also moving towards the center of some galaxy, and the whole galaxy is moving towards the center of some other thing. So that's how everything is. But then, if because of the varying length scales, the movement of something very big and very far away might not necessarily translate to a very big movement when it comes to our own scale. So for all practical purposes, it might be not a big source of error to assume that maybe the stars are fixed in the sky, but they're actually moving. So that is just to show the to give us a real feel of the sentence that gamma is only defined for some time or epoch. That is, the vernal equinox line is defined for some time or epoch. So, for example, table 4.2 shows the celestial coordinates of the star Regulus. I think we saw Regulus. So if we go back, let's go back and get it. That's Polaris, the polar star. Look at how big it is compared to the sun. So that's the sun. Yeah, this is Regulus, this one. Look at how big it is relative to the sun. So that's the Regulus we are talking about here. So currently shows the celestial coordinates of the star Regulus at 5 epochs since AD 1700. So people have already started making correct observations of the night sky, and then determining the orbits and positions of heavenly bodies ever since that time ago. So currently the position of the vernal equinox in the year 2000 is used to define the standard grid of the celestial sphere. So because we know everything is in constant motion, but we still have to make our own engineering calculations, so it's always good to maybe define the position that will be used for a length of time, and then you make corrections for the known changes in such position with time. So at the time of writing this textbook, this version of the textbook, the vernal equinox lies, the vernal equinox position in the year 2000 is in current use, and I think it's still in current use until now. So we see that it varies quite. It has varied from about 13 degrees to about 11 degrees. So it's actually moving over the space of about 300 years. So in 2025, the position will be updated to that of the year 2050. So there's been a way that we are able to calculate positions of all these kinds of heavenly objects, and that is just from equations of two-body motion or the n-body motion that we've learned arising from Newton's law of universal gravitation and then Newton's second law. All that we learned in orbital mechanics 1A 313, and with such knowledge you can always try to make calculations into what positions heavenly bodies might have in the future, and with that the position of the vernal equinox will be determined 25 years into the future, and then such position will be used to make calculations of the movement of other measurements of the movement of other heavenly bodies or satellites in the sky. In 2075, the vernal equinox will be updated to that of year 2100, and so on at 50-year intervals. Since observations are made relative to the actual orientation of the Earth, these measurements must be transformed into the standardized celestial frame of reference. As table 4.2 suggests, the adjustment will be small if the current epoch is within 25 years of the standard precision epoch. So we'll quickly look at the state vector and the geocentric equatorial frame. You know what state vectors are. Those are the position vector, the velocity vector, the acceleration vector. The position vector, the velocity vector is the differential of the position vector with time. The acceleration vector is the differential of the velocity vector with time. That means the acceleration vector is the twice differential of the position vector with time. So we move on. So think about the familiar assumptions. I'm not going to say them now, but you know the assumptions, and think about them. Think about them, and try to see if you are very comfortable with thinking about them and then understanding them. But this is the familiar two-body equation from orbital mechanics 1, and that is r dot dot is just the acceleration vector, and that is r, that's the position vector, where r here is the magnitude of the position vector, and mu is the gravitational parameter of the dominant gravitating body in the two-body system. So we see the components of the position vector, and especially those of its time derivatives, must be measured in a non-rotating frame attached to the Earth. Why do you think this should be measured in non-rotating frames attached to the Earth? It's just for us to be able to get their absolute values. Their absolute values. When if they were to be measured in a body fixed frame of reference, like a fixed frame of reference onto the satellite, then whatever measurements are made will only be relative values. They won't be absolute values. So if we had an inertial frame of reference, a geocentric inertial frame of reference, then we can make such measurements relative to that frame of reference. So a commonly used non-rotating right-handed Cartesian coordinate system is a geocentric equatorial frame shown in figure 4.5. So this is what we learned about this in the first slide of Orbital Mechanics 1A 313. We learned about relative motion with respect to the non-rotating Earth. So all those equations that we arrived at are valid for our discussions now of the movement of satellites. So this is something that is common to use, geocentric equatorial frame, where the vernal equinox line defines the x-axis, and then the z-axis is normal to the equatorial plane and the celestial equator, and then the y-axis is at right angles to the x-axis. So we move on. The x-axis points in the vernal equinox direction. The xy plane is the Earth's equatorial plane. The z-axis coincides to the x-axis of rotation and points northward, which is very clear from this picture and then from our knowledge of how everything is situated in space. The unit vectors IJK, this time in capital letter, because we are just to make them different from other kinds of Cartesian coordinate systems, just to be able to show that these are reference to the celestial frame, geocentric equatorial frame, which is used with the celestial sphere. So the unit vectors IJK form a right-handed triad. The non-rotating geocentric equatorial frame serves as an inertial frame for the two-body Earth satellite problem, as embodied in equation 4.1. But it is important to note that even such a frame of reference is not truly an inertial frame, since the center of the Earth is always accelerating towards a third body, the Sun, to say nothing of the Moon, a fact which we ignored in the two-body formation. You know, when we say two-body problem is just a problem of determining the motion of two bodies solely under the mutual influence of mutual gravitation, solely under the influence of mutual gravitation. So we were neglecting the fact that there might be other dominant forces of attraction inside the system, and that would be the n-body problem, which we saw was quite chaotic and not periodic. So in order for us to make some kind of very nice engineering calculations, we just assume other things are not affecting the two-body problem of interest that we are studying. So, so in actual fact, one might not exactly have a truly inertial frame of reference, because if we were to shift our frame of reference to the center of the Sun and think it might be fixed, and I just told you like moments ago that even the Sun even the center of the sun is accelerating towards the center of some other thing. So if we try to shift that inertial frame of reference to the center of that thing that the sun is accelerating towards, that thing is also accelerating towards the center of some other thing. So putting the center of the Earth as the center, the origin of some fixed inertial frame of reference might just be good enough for the engineering applications in our own length scale. So in the geocentric equatorial frame, the state vector is given in component form by R equals xi plus yj plus zk. That is R. If something is positioned there, the position vector is R, and then it will have components in the Z direction, and then components in the X direction, and then components in Y direction. That is xi, yj, zk. And then the velocity is just the differential of the position vector, so vx, vy, vz. So it has some component of velocity in the X direction, in the Y direction, and then in the Z direction. If R is the magnitude of the position vector, then of course, using vector notation, we will have the position vector to be R, or to be equal to the magnitude times the unit vector in the direction of the position vector. So from this figure, we see that the components of UR, the direction cosines of R, are found in terms of the right ascension alpha and declination delta as follows. So if we try to see how this come about, we know that if we have a vector, a vector, the position vector to be R equals U, R, that's the magnitude, then U R. Then U R is just equal to, that is the unit vector, is equal to the vector divided by the magnitude. So that if you have the vector to be in this case x I kappa plus y j kappa, that's supposed to be capital Y, plus z k kappa. All we have to do is just divide by the magnitude of the vector so that we can write the unit vector in terms of its directional cosine as, let's use L for x over R, and then use M for y over R, and then use N for Z over R. So we've just expressed the unit vector in the direction of the position vector in terms of its directional cosine L N N, where L is equal to x over R, n is equal to y over r, and n is equal to z over r. And then from this diagram, we can see that the unit vector r, will also be, or the component of r in the z direction is equal to r sine delta. That is, component of r in the the component of the unit vector ur in the z direction. In the z direction, the component of the unit vector, that is the directional cosine of or the correct direction cosine of the unit vector ur in the z direction is just equal to sine of this declination angle, so sine delta. I hope you are getting what I'm saying. That if you want the component of ur is along this axis. So if you want its component in the z direction, you just have to find the sine of this angle, sine delta. So that what we are saying is n. So what we are saying is n equals sine delta, and then the component of r in the equatorial plane is the component of ur in the equatorial plane is just the cos of delta. So cos delta. So cos delta. So if we now want the component of, so this line here, ur in this plane is going to be cos delta. So if we want its component in the x direction, we just have to do cos delta sine alpha. That is the right ascension there. So we have L then to be equal to cos delta sine alpha. Sorry, cos delta sine alpha, and then m is going to be cos delta. Let me just check to be sure. So if this is cos delta, sorry, I've made a mistake. This is cos delta cos alpha, and then n is cos delta sine alpha. So as can be seen from here. So if the component of ur in this plane is cos delta, then the component of ur in this axis will be cos delta cos alpha. Then in that y direction it will be cos delta sine alpha. So these are direction cosine of the unit vector in those directions. So when we have written it that way, that means we can directly write that ur. So if you just substitute all this for x over r, y over r, and z over r, or l, m, n there, we have ur to be equal to cos delta cos alpha I plus cos delta sine alpha j And these are capital letters, so plus sine delta K. So that means the position vector R is equal to R, the magnitude, times all this. So because I don't want to write again. So the magnitude times all that. So that if we have the vector, we can find its magnitude and then try to find its direction cosine and then try to determine its declination and then its right ascension from this, because from here this implies that delta, which is the declination, is equal to arc sine n, right? And then and then we see that cos alpha is equal to L over cos delta. So obviously we can find the right ascension from J. That is, the right ascension alpha equals arc cos L over cos delta. So in the, I suppose on this PDF it doesn't have some of the more explanation that the later version, which I have with me here, has. And we just note that since delta is arc sine n, there is no quadrant ambiguity by definition, since the declination lies between minus 90 degrees and then plus 90 degrees. That means delta, once you have, when you do arc sine n, it's going to give you a definite value of delta, and you are going to be able to define the actual declination angle. Because if you find arc sine n and it gives you positive, then you just know you are in the northern celestial hemisphere, and if it gives you a negative value, you know that you are in the southern celestial hemisphere. Then since cos delta cannot also be negative, I'll just advise you to go and read the rest of this portion in the later version, because I'm really running out of time here. So we just go on from figure 4.5, we see that the components of U are the direction cosines of R are found in terms of the right ascension alpha and declination delta as follows, the way that I've just shown you in my notebook here. Therefore, given the state vector, that is, we given the position vector and then the velocity vector of a satellite, we can then compute the right ascension and declination. That means once you know the position vector of a satellite, then you can directly compute its right ascension on the celestial hemisphere and then its declination on the celestial hemisphere. However, the right ascension and declination alone do not furnish R. That means for you, if you just know the right ascension and then the declination, you can't directly get the position vector. However, if you have the position vector, you can directly go from that to get the direction cosine that is to find the right ascension and then the declination. This is what we are saying. Here, because we have the position vector, we're able to work our way downwards and get the declination and then get the right ascension. But if we just know the right ascension and then the declination, we might not be able to work our way back. Because obviously, if we know the right ascension and declination, we would only be able to compute UR. We still won't know what R is. So we won't be able to get the position vector. R we know is given by Kepler's first law as A squared over mu 1 over 1 plus E cos theta, where theta is the true anomaly. That means for us to be able to define the orbit or the state vector of a satellite, knowing its declination and then its right ascension alone will not give us enough information to be able to get its position vector. So we still need further information about maybe its eccentricity, the true anomaly, its specific angular momentum, or some other parameters which we shall be talking about shortly. So obviously we can write a MATLAB routine to code this, so that once you have once you input the position vector of the satellite, it can just compute for you the declination and then the right ascension of the satellite. And I want to leave that as an assignment for you guys. The textbook, that is the newest edition which I have here, and then which you have in the library, has got the algorithm, and then there's so you can go and check the textbook, and then I think it's even already done it in the appendix, but I would want you to go through doing it by yourself, because then will be the only time that you'll be able to learn anything. I've wanted to even start it here, but I'm really running out of time here. So that's an assignment for you. Go to the textbook on page 193. Try to try to compute the algorithm 4.1 in MATLAB, and then send to me. You can consult yourselves on this assignment since this is the first one, but make sure you send them to me individually and put your names on your own code. We'll try to quickly look at try to quickly finish up by looking at this example. So, example 4.1, if the position vector of the International Space Station is R equals that. So this is relative to an inertia, a geocentric inertia, and equatorial frame of reference. And then this is how you see it on the sky. In the sky. What are its right ascension and declination? So what we just go to do is find the magnitude of the position vector. So we found the magnitude, that is the distance away from the center of the Earth, and then we find the unit vector in that direction. And then once you have found the unit vector, we can see that which was n, is just equal to sine delta, and then delta is just equal to arc sine of that. So immediately we found delta. That's the declination. There's no, this is what I was trying to get about. There's no quadrant ambiguity, since by definition the declination lies between minus 90 degrees and plus 90 degrees, which is precisely the range of the principal values of the arcsine function. It also follows that cos delta cannot be negative, because cos 90, between the range of 90 and minus 90 degrees, then cos delta is a positive, or cos of the angles between the range of going from 90 to minus 90 degrees is always going to be positive. So from equation 4.5, that is this equation, we were able to get that cos delta. We've already calculated for delta, so we know what cos delta is. And then cos alpha, cos delta cos alpha will be equal to that from equation 4.5. So that cos alpha is equal to this, and a negative sign. But alpha might have the quadrant ambiguity because it varies between 0 and 360 degrees. So in order to actually know the one you are talking about, one might need to do to see the sign of this direction cosine. Read the textbook more. I'm running out of time. I can't make enough explanation of that, which implies the right ascension is equal to the second quadrant or equal to that third quadrant. On C, yeah, that is what I was trying to drive at. We observe that sin alpha is negative, which means, because cos delta cannot be a negative value. So if this is negative, then the sin alpha is negative, and for a negative sin alpha, then cos alpha will give you a value in the third quadrant. So that's 198.4 degrees. So if we are provided, so that's a good enough example to show that once we have the position vectors, we can work away and get the declination and then the right ascension of the orbit. So if we are provided with the state vector at some point, R0, V0 at a given instant, then we can determine the state vector at any other time in terms of the initial vector by means of the expressions. R equals F R0 plus G V0, V equals F dot R0 plus G dot V0. I hope you still remember F dot G G0 are the Lagrange coefficients. The Lagrange coefficients. And I hope you remember that we use the Lagrange coefficients to determine the position vector of a mass on an orbit at a later instant in time, given the initial values of such position vectors. So specifying the total of 6 components of R0, V0 therefore completely determines the size, shape, and orientation of the orbit. So that means in order to describe the orbit, the size, shape, and orientation, we need some initial values, and then we can use the Lagrange coefficients, and then we can also get the declination and then the right ascension. You can go through example 4.2 on your own, because I'd like to end the lecture now. It's almost 2 hours. Go through the example on your own, so that we'll be starting. So go through the example, and then you just read this concluding paragraph of the section we just treated, so that it will set the stage for orbital elements and the state vector, which we will be treating in the next video lecture. The previous example illustrates the fact that the 6 quantities of orbital elements comprising the state vector R and V completely determine the orbit. That's what you should strive to understand from this lecture and then from the workings of the examples there. Other elements may be chosen. The classical orbital elements are introduced and related to the state vector in the next section. So please do the assignments which I've given you and try to send them to me via email, and then also try to send in your feedbacks, comments, and questions on the lecture, and maybe suggestions on how to make it, how to give it a better experience, and I'll make it a better experience. And like I've told you, subsequent slides, I might be adding some more to this slide, or I might be making subsequent slides at the same time that I'm making the video for the lecture. So I hope you use these videos to study well, and then I hope you stay committed to your studies. So have a nice time. Remember to send me feedback, comments, and questions. Thank you.